That's not it. There we go. You'll get used to doing this kind of stuff. And you need it. If you want to be a good inorganic chemist, go to a lecture and follow what's happening. You really need to be able to count electrons. Okay. So we're going to talk organotransition metal chemistry. So this is the chemistry of compounds with metal carbon bonds. And large ligand fields. This is going to be about the 18 electron rule. You're used to the octet rule. And we're going to do the 18 electron rule. And it comes from S2P6D10 electronic configurations. So transition metals have those valence orbitals available to them, and happens to be the case that they often have 18 electrons in their valence shells. Now, I should say that many compounds violate this rule. We'll call them many hypovalent compounds. Okay, especially the 3D transition metals. So 4s and 4p are higher than 3D by a significant margin. And so they don't really participate in the bonding as well. And sometimes in the 3D transition metals, you'll see 12 electron compounds instead. You just have the S and the Ds. All right, so one of the things we want to know when we look at a transition metal compound is the number of valence electrons. And if you count up that number, it tells you whether or not the compound is hypovalent or not. You know, hypovalency defines all kinds of reactivity. You know that boron trifluoride is a Lewis acid, and it binds ligands like diethyl ether. Not a very good ligand, but it sticks to boron because boron doesn't have an octet. And you know that carbon monoxide has a triple bond because carbon doesn't have an octet. So transition metals, same issue. You want to know whether or not they're hypovalent, okay? Now this can be tricky to figure out. And you need to be able to do valence and electron counting. Okay, so we're going to do a few examples here just to get us back up to speed on this topic. So we take a boron and we mix it with 3 fluorines. You end up with boron trifluoride. And if you add ammonia to that, then you end up with this ammonium borane complex. And we said that this is a dative bond from the ammonia to the boron. And one of the terms that you're going to need to know is that these fluorines, because they make a bond to the boron using one electron, we're going to call these guys X-type ligands. And ligands that make a bond, a dative bond, are called L-type ligands. Right? So an L-type ligand is a ligand that provides both of the electrons. An X-type ligand is a ligand that provides one. All right. X-type ligands donate one electron. Now, some of you might say, wait a minute. Fluorine is fluoride. It has an octet. So why is it only donating one? This assumes a neutral ligand, not an anionic ligand. Okay. So it's a fluorine, not a fluoride. We're talking neutral fragments. Okay. So let's do another one. L-type ligands. Donate 2 electrons. There's one more. They make dative bonds also, Z-type ligands, but they don't donate electrons, they accept electrons. Okay. Okay, so 3 different kinds, 1 electron, 2 electrons, or 0. Let's also define what we mean by valence. So this is a term that people use slightly differently, but this is the correct way, the rigorous way. Number of valence electrons used to make bonds. Okay, so valence is equal to the valence is the number of valence electrons minus the number of non-bonded electrons. So the boron in BF3 is trivalent. The nitrogen in ammonia is trivalent. the nitrogen in ammonia borane is pentavalent. The boron is trivalent. Yi-Chung, you frowned at the screen. Why did you frown at the screen? Does that bother you?
No, I see it now because of the charge, right? Although you wouldn't think of nitrogen as pentavalent.
Why not?
I mean, normally you would never see like nitrogen with like 5 bonds, right? But I guess like it's a formalism because of the charge, so it could be like 5 bonds in that sense.
It's important to know what we mean by valence, right? This is why I'm asking, is that people, they kind of have this loosey-goosey idea of what it means. And this definition is rigorous, okay? So number of electrons used in bonds is the valence. And it seems strange to make nitrogen pentavalent, but there's nothing strange about it. It just means something different than what you have in mind, probably. So that's why I picked on you, because everybody's sort of in the same boat. What? Pentavalent? So the reason we're going to define it this way is that I want to talk about the differences between valence and oxidation state. The oxidation state is the charge, typically on a metal, that is assigned by analyzing electronegativity. So, for example, boron trifluoride, we get 3 normal covalent bonds. It's trivalent. And fluorine is more electronegative. Than boron. And we therefore say, it's like a fluoride minus, and the boron is like a boron plus. And since there are 3 fluorides, you say boron in the plus 3 oxidation state. Okay, no big deal, right? But let's stop for a second and ask, what does that really mean to say that? Are you saying that the charge in the boron is 3 plus? There's no charge, right? What do you mean there's 3 plus? Well, it's just a nomenclature. It's just a formalism, right? Fluoride's minus, so the boron's plus. There's 3 of them. It's boron 3 plus. But that's not really the charge. I mean, to define the charge, you have to look more carefully and in detail. Which means things get complicated. The nice part about valence, and we're going to come back to this, is that valence is unambiguous because the reference is very well defined. It's what does the gas phase atom have? It has 5 valence electrons or 3 valence electrons. How many bonds are there? Sometimes the number of bonds is a little bit ambiguous, but it's a simpler system. And I'll show you an example of why here. Okay, so let's do methylene chloride. Okay, What's methylene chloride? Another name for methylene chloride is dichloromethane. So you've got 4 normal covalent bonds. Carbon is what's the valency on carbon? It's tetravalent. What's the oxidation state of carbon?
Zero.
You're the first person to have answered correctly, Yi Chung. It's 0, actually. Most people, so when I interviewed for my position at Columbia, Jed Parkin took me out for dinner the night beforehand. And he said, what's the oxidation state of carbon and methylene chloride? And I said, 2+. He said, oh, that's interesting. What did I mean? 2+. My reasoning was, hey, you know, hydrogen and carbon, they're similar in electronegativity. So I wouldn't assign a positive charge for those atoms. So the chlorine that's most electronegative. So, you know, 2+. But that's not what oxidation state is. Oxidation state is a formalism that says if carbon is more electronegative than hydrogen, you assign it a minus charge and the hydrogen gets a plus charge. And that's true. The electronegativities are such that carbon is in the 0 oxidation state. So I'll just say. Yeesh. Let's try this again. Now, I'll tell you, saying that carbon is in the 0 oxidation state bothers most people. Doesn't feel right. And I think it's because most people use oxidation state to mean valence. Okay, but oxidation state is different than valence. Oxidation state is a measure of relative electronegativities. All right. Oxidation state can be very confusing for this reason. Things get really tricky. Life gets hard when you get into fancy compounds. So valence is a little bit less ambiguous, okay? All right, let's do some more interesting ligands here. We're gonna do a bunch of different ligands and show you how to analyze their bonding. Start with allyl. Got manganese, pentacarbonyl allyl complex. It's a good one. You shine a UV light on it, carbon monoxide will pop off. And it makes this cool compound here. This tetracarbonyl. And it has an allyl bonded like that. I'm going to redraw that just a little bit more carefully. Where, what does that look like? What is that thing? That is a allyl fragment that makes 3 connections to a manganese center. Okay, so this guy is sort of simple, normal covalent bond. what is going on with that guy? So this thing here, we've got CO5 manganese, and I'm going to write it out like this: A to 1 C3H5. This one here is CO 4 times manganese, A to 3 C3H5. A to 3 means 3 connections. This is an X-type ligand. This one is an L comma X type ligand. So here you have both a dative bond and a normal covalent bond. Okay, so just to make it clear, eta refers to the hapticity, or the number of atoms. So just to, this thing can actually be redrawn like that. And there you got a double bond in the electron pair in that pi system binding to the metal center. And it turns out that there's another resonance structure you can write like that, with the double bond on the other side. The arrow represents a dative interaction. Okay, so you can think about Al as an LX, but you can also think about it kind of like that. An Al fragment is like a little tiny conjugated system, and you can think about the manganese overlapping with all 3 p orbitals. And in this sense, you can say that C3H5 is X3. If you make 3 normal covalent bonds. So it's often the case when you have like a eta 3 type thing or eta 5 that all the connections are equal, but not always. And in this allyl case, for example, not all 3 carbons make the same kind of connection to the metal center. Let's take a look here at cyclo pentadienyl ligands. Yikes. Sometimes they can be A to 1. There's an A to 1 cyclopentadienyl ligand. There's another way that these things can bind. Not very common, but it happens. That's another A to 1. Okay, so you can just make a single metal carbon bond. Two different types, the sp3 one and the sp2. Here's another version. Now we're doing A to 3. So what is that? A to 3 is rare. Don't really see that very often. It's like an allo. And then the beloved A to 5. Common. Here we've got two double bonds binding as L-type ligands and one normal covalent bond. You could also say it's X5, but people tend to describe this as a 1- fragment when it's off the metal. Cyclopentadienide is a stable anion, and so, you know, it basically makes one X-type connection, and then there are these two other L-type connections. So it's like super allo. So when you look at these kinds of fragments and the metal center, you can analyze the bonding and make a decision about the number of valence electrons that are being used to form the complex, okay? So we're going to use the LX formalism to do electron counting. And in particular, we want to know if the transition metal center is open shell or not. What does that mean? Open shell means does not have 18 electrons. Okay. 18 electrons is considered a closed shell compound. You can't add any more electrons to the valence shell of a metal center with 18. All right, so let's do an example here. So we're going to start off with iron tetracarbonyl dihydride. So what we want to do is to count the valence electrons is to break this thing into neutral fragments. Let me repeat that. To count the electrons, you must break the compound into neutral fragments. We're going to do a version where we break it into charged fragments later, but the way we're going to do it in this class, and the way that is better, in my not so humble opinion, is to break the compound into neutral fragments. So we're going to get 2 hydrogens. We're going to get an iron, and we're going to get 4 COs. 2 hydrogens, each with 1 electron, contribute 2 electrons. How many valence electrons does iron have? If you're looking at the periodic table, you have a problem. You must know this off the top of your head. Iron, ruthenium, and osmium, really useful one to remember because it kind of divides the periodic table. 8 electrons for iron, ruthenium, and osmium. Nickel, palladium, platinum, 10 electrons. That's the right-hand side. Titanium, zirconium, hafnium, 4 electrons. That's not the left edge, but close. All right, so 2 electrons for each carbon monoxide, right? Carbon monoxide brings 2 electrons in its lone pair, donates them to the metal center. So there are 4 of those. So we get 8, 8, 8, and 2 is 18 electrons. So closed shell. Not hypovalent, not hypervalent, closed shell. Okay, so, right, 18 electrons means that the iron center involves the 4s and the 4p and the 3ds in making bonds, according to a covalent picture. We know natural resonance theory can be used to kind of supplant that. Osmosine, it's a good band name. We are going to break into neutral fragments. Osmosine. 8 electrons for osmium, same column as iron. And we have 2 cyclopentadienyl ligands, CPs. How many electrons per CP? Well, we just said that a cyclopentadienyl ligand is an L2X. Makes 1 normal covalent bond and then uses 2 dative bonds from the 2 pi bonds. So L2X is 5. Each L is 2 and X is 1. It also happens to be the number of carbons in the pi system that are making connections to the osmium. Remember how allyl can be described as an X3? Each carbon contributes 1 orbital with 1 electron. Benzene, 6 carbons, 6 p orbitals, 6 electron donor. Okay. So CP is 10, osmium is 8, 18 electrons again. Closed shell. So 8 of 5, CP donates 5 electrons. There's the neutral fragment. L2X. All right, so some people like to use an anionic formalism, okay? We've talked about the metal being metal plus and the ligands being ligand minus. If you do that sort of an analysis, now you have an osmium That's 2 plus and 2 CP anions. How many electrons for osmium 2 plus? Well, you got to first start by saying, all right, I know osmium has 8. If this is, I counted the oxidation state up, and this is a 2 plus osmium. So that means there are 6 electrons there. How many electrons per CP anion? Well, you might know that CP anion is aromatic. So it has 6 pi electrons. So 2 of those is going to be 12 electrons total. Add those up, and you get 18 electrons again. So it returns the same answer, but you must count the charges on the ligands and the metal center before you do the arithmetic of adding them up. And the problem is that sometimes it's not clear what the charge on the ligand is. And there are actually different resonance structures that you can write that have more or less charge on the ligands. And so you both have to assign the resonance form of the compound that you're interested in. Well, yeah, you have to assign the resonance form of the compound that you're analyzing to do the electron counting and the charge formalism. And sometimes it's straightforward and sometimes it's not. So the neutral ligand formalism is generally not what people reach for intuitively, but it is a simpler method of counting charge. Let's do another cool one here. I like this guy. So here's an iron. Tricarbonyl with a cyclobutadiene on it. Let's do neutral formalism. 8 electrons for iron. We have an 8-4 cyclobutane ligand. How many electrons for that? Well, same system. It's 4 carbons each with a p orbital. There's 4 electrons for that thing. And we have 3 COs. That's 6 electrons. And again, we have an 18 electron compound. So how do you think about the cyclobutane? Well, it's 4 electrons. You could say it's an L2 ligand. This is a cool one here. We're going to take tantalum. And we're going to stick this interesting looking compound on it called trimethylene methane. This guy is A-4 C4 H6 trimethylene methane. So, yes, and then this molecule also has some methyl groups on it on the tantalum center. So let's do the electron counting. We have what we call a CP star ligand here. That CP star is just a cyclopentadienyl ligand that has 5 methyl groups on it, each of the carbons. So this is still a 5 electron donor, excuse me. Tantalum, 5 electron donor. We have 2 methyl groups. How many electrons per methyl? One each. Neutral fragments, so you got to cleave the bond in half in that case. And then what do we do with this A to 4 C4H6 thing? Any guesses?
I have it, but it's just a guess, and the guess is like it's just from like watching the pattern of like what we've been writing, and that is that anytime we see to have that, you're calling it an allele, it looks like a mu or a xi or something like that. Every time the exponent always seems to match the amount of electrons that it has for valency. So 4 electrons.
Good guess. Good guess. So it's 4 electrons. Now let's analyze why it's 4 electrons. So this thing can also be written this way. And it can also be written this way. And there's one more orientation of that double bond. But it's kind of like an allyl fragment, except you got another CH2 dot hanging off of one of the other carbons. This thing it's got these 4 p orbitals all lined up. It's kind of planar and in resonance. Not a stable compound, it's 4 electrons, but on the metal center, it is. So how would you do that one in an oxidation state land? I guess you would call that fragment a 2- fragment. And this would be tantalum 5+ then. All right, let's do another one. Nickel diallyl. I once stayed up 2 nights in a row trying to make the platinum version of this compound. I failed. Two of these A to 3 allyls, 3 electrons each. This compound has 16 electrons. It's open shell. It's diamagnetic. I'm going to say it's hypovalent. Hypovalent really means there's an empty orbital somewhere. Here's a good one. Tungsten hexamethyl. It's a fireball, that molecule. How many electrons does tungsten have? 6 electrons, Mac. Chromium, molybdenum, tungsten. Thank you, sir. Chromium, molybdenum, tungsten are in a column. 6 electrons for chromium, molybdenum, tungsten. We got 6 methyls. $12 electrons total. So this guy's got space. Let's take 6 more. Amazing. So tungsten uses all 6 of its electrons to make bonds with those methyl groups. And you got your EG here, and you got your T2G. These guys are sigma star, and this one is non-bonding. All 6 of the d electrons on tungsten have been used to make those bonds, so there's no d electrons left. No d electrons remaining, which means that you have empty non-bonding orbitals. Right? It's like borane. No. Let's look at tungsten hexacarbonyl. Tungsten has got 6 electrons, you got 6 COs, that's 12 electrons, right? Each carbon monoxide brings up 1 lone pair. You got 6 of them, that gets you to 18 total. In tungsten hexacarbonyl, you got pi, sigma star over pi, and the 6 electrons are still on the tungsten center. It's tungsten, it's not tungsten 6 plus here, it's tungsten 0. It didn't use electrons in making the sigma bonds, and so they do sit in those pi symmetry orbitals, though, and they do make pi bonding interactions with the COs. Totally different compound, hexamethyl and hexacarbonyl. Tungsten hexacarbonyl is stable in air. Tungsten hexamethyl bursts into flames in air. Sometimes you have to account for formal charges. Look at this guy. You could write this formula, this, A to 5, C6H7, FeCO3 minus. So iron is 8. We now have a minus charge, formal charge, not a formal charge. We have a minus charge on this fragment. We're going to add that to the pile. That's a 1. Each negative charge gets a 1. We've got an A to 5 C6H7 fragment. How many electrons for that thing? Using Mach's principle, A to 5 C5H7 is going to have 5 electrons, 1 for each of the carbons that's fastened to the metal center. And then we have 3 COs, 6 electrons. This guy comes in at a whopping 20 electrons. Something is wrong. The molecule is probably not stable. It's more likely not a tricarbonyl. It's more likely a dicarbonyl. Okay, so if you see somebody draw that structure, I watched Dean Tost do that. Dean Tost, professor at Berkeley, he gave a sort of mock interview at Caltech when I was a graduate student. And he was talking about his projects that he had in mind, and he drew a 20 electron compound on the chalkboard, and I saw it and I thought, I should say something. I should say something. I kept my mouth shut. Wouldn't have mattered anyway. But this is how you use that. You know, you look at those compounds and you say, does this make sense? All right, let's do another one. Bis triethylphosphine, cobalt, dicyanocarbonyl anion. How many electrons does cobalt have?
9.
9. There we go. Nickel, palladium, platinum is 10. Cobalt, rhodium, and iridium is 9. Iron, ruthenium, and osmium is 8. Cobalt, rhodium, and iridium, 9. We got a negative charge on there, so we got to throw on that charge, that one extra electron for that charge. 2 cyanos, 2 electrons. So wait a minute, cyanide is an anion. Why only 2 electrons for if we have 2 cyanide anions? Because we're doing neutral ligands here, not charged ligands, neutral ligands. It's going to be a cyanyl radical, so to speak. Okay. 2 electrons, 1 for each cyanide. Carbon monoxide is an L-type ligand, brings 2. Triethylphosphine brings its lone pair to make a dative bond. 2 of them, that's 4. 18 electrons. Cyanide or cyanyl is X, CO is L. All right, so one of the tricks, charged compounds throw people off a little bit. One of the tricks you can do to do the math on this is to sort of mix the formalisms a little bit, okay? So let's just do a mental experiment here. Let's pull off a cyanide. Okay, and I'm going to do that because I'm going to just rip that negative charge off with it. It's kind of nice to say, all right, there's an extra cyanide anion stuck to this cobalt center. Now we can do the counting over here. So we got cobalt at 9, we got a CO for 2, a cyanide for 1, and 2 triethylphosphines for 4. That's 16 electrons. And this guy is 2 electrons. Add those together, it gives you 18 electrons. So it might be easier, and it will get easier to count oxidation state, especially when you use this technique where you could pull off a cyanide anion from the molecule just in your mind's eye. And then, say that's 2 electrons. Thinking about it as kind of like a negatively charged 2 electron donor. You pop that off and then you look at what's left. It might be easier to count the charge of, or count the electrons of what's left. And then remember that we're interested in the molecule on the left, not the one on the right. So you've got to bring those 2 electrons back into the valence shell. The cyanide lone pair comes in there to make kind of like a dative bond using a negatively charged fragment. Be careful not to get too loosey-goosey with your language there, but that cyanide, when it comes and sticks to the cobalt, brings both of those electrons up. On the left, in the previous example, we counted this guy as 1, and then there was another 1 hiding inside of the cyanide there. Sometimes it's nicer to think about it as having 2 electrons in its lone pair. And you can eliminate that charge by taking that step, simplifying the count on this thing. Okay. All right. Let's do some complexes with metal-metal bonds. So we've got this rhenium bonded compound. Who else is in rhenium's column? Manganese and technetium. Wild and crazy technetium. Anybody know what technetium is used for? There's a technetium compound patented by inorganic chemists at MIT that is sold under the brand name Cardiolite. It's a radioactive substance. Technetium is radioactive, and it's very emissive. And they put this technetium compound into you and look at your heart. When you have a heart attack and they want to detect a blockage, it's used as an imaging agent. So let's do this rhenium compound. Rhenium, manganese, and technetium are all in the same column. So we're going to call this rhenium A and rhenium B for a second, and we're going to start by counting these. We have 5 times 2 electrons here, and we have 7 electrons here. And you can think about this whole fragment as being like an X-type ligand. To rhenium A. So it donates 1 electron. So rhenium A has 7. 5 COs get you to 10. And then the CO 5 times rhenium B compound brings 1. That's 18 electrons total. You can also count everything. And divide by 2. Okay, so you could say 2 rheniums, 10 carbon monoxides, and 1 rhenium-rhenium bond. Okay, because you got to include the 1 rhenium-rhenium bond if you're going to do this trick, because the 2 rheniums are raising each other's electron counts. You don't include that interaction, then you won't identify the appropriate valence. So we have 7 electrons per rhenium, that's 14. 2 electrons per CO, that's 20. 1 rhenium-rhenium bond is 2 electrons. Each rhenium is getting an electron from the other one. So this is 36 divided by 2 equals 18 electrons per rhenium. Okay, so I'm going to stop there. And I'm happy to stick around and answer any questions you guys have. And if not, then I will see you, or does somebody want to ask a question for the rest of the class to hear now? And if not, I will see you on Wednesday. Terrific.